Good morning. Today I'd like to talk about line integrals, which are yet another type of integrals that we will look at. These are going to be integrals not along the x-axis, not along area in the plane or surface area. These are going to be integrals that are performed over curves in either two or three-dimensional space. So before we get going, I want to remind you a little bit about what a curve is. We haven't made a huge deal out of this distinction so far, but now we do have to. A curve is a set of points in the plane or in three-dimensional space together with parametric equations that describe the points. For example, if I have a circle of radius 1 centered at the origin, the circle is the graph. I have to tell you the equations that go with that. So I could say that x is cosine t, y equals sine t. T could be anything from 0 to 2 pi, and this will trace the circle out in a counterclockwise direction. We've seen before that there are other ways to describe the circle, so this is one of them. Also, we say that a curve is smooth if the derivative of x with respect to the parameter and the derivative of y with respect to the parameter exist for all t values in the interior of the interval from a to b, and also that there is no t within that set of t values where the derivatives both are zero at the same time. You'll remember from the discussion of vector valued functions that this is useful to us because this means that the velocity vector tells us the direction that the curve is going in at the given t value. Sometimes it will be useful to deal with curves that are not actually smooth every place, but can be carved up into a finite number of pieces which are smooth. The simplest example that I can think of is you can imagine wanting to start at the origin, travel horizontally along the x-axis until you get to x equal 1, then from there travel vertically parallel to the y-axis until you get to y equals 1. Obviously, this is not smooth because of the sharp corner. There is no well-defined tangent line there. On the other hand, this lower part all by itself is smooth. This upper part is smooth as well. Visually, that is. I still have to cook up formulas that will give me these little bits that I'm looking at. But the thought is, even if I have a sharp corner like this, maybe I can carve the thing up into nicer pieces. For the first piece, since I'm traveling parallel to the x-axis, in fact, I'm on the x-axis, it makes sense to use x as the parameter. So I'll set x equal to t. For this part of my curve, the y coordinate is always 0. The x's range from 0 to 1, so I'll want my t values, which are x values, to range from 0 to 1 as well. So x will be t, y will be 0, t will be allowed to vary between 0 and 1. The simplest way I can think of to describe that first piece is by vector valued function r of t is ti plus 0j. Of course, this won't get me the entire graph that I'm looking at. I've got to make a sharp turn and go upwards now. There's always a little bit of fiddling around to do. In my description, t is 0 here, it's 1 here. I'm going to want to write down some sort of formula that starts off with t being 1, and ends with t being any particular finite value that I want, but I want to rig it so that at the end, however I decide to do this, I'm at y equals 1. For this part of the curve, the x-coordinate is always 1, so I'll just write x equals 1, and I'm going to let y equal to t minus 1. I had to fiddle with it a little bit here. When t is 1, that's going to make the y-coordinate 0, which will make you be at this position, which is where you want to be, because that's where you stopped here. If I want to allow the y to increase until the y-coordinate's 1, I would want some t value so that t minus 1 was 1. That would mean that the t would have to be 2 in that case to make this work out correctly. So for this second chunk, my x-coordinate will be 1, my y-coordinate will be t minus 1, and the t in this piece varies from 1 to 2. The vector valued function that describes that part of the graph is this. So putting it all together, I've got what amounts to parametric equations, vector valued functions, which describe the location of points on my curve. Depending on whether or not t is less than 1, I could use this one, or I could use this one, depending on whether I'm looking at that piece or that piece. This is what we mean when we say that a curve is piecewise smooth. Imagine that you have a piece of wire. It could lie in a two-dimensional plane or in three-dimensional space, and the curve occupied by the wire is at least piecewise smooth. The wire might have a varying mass density that goes from point to point. I'll call the mass density F of x and y, kilograms per meter of the material, for example. If I were to literally tell you equations that produce the graph of the curve, then the question, what is the total mass of the curve, can be handled in a way that's very similar to what we've done before. We would imagine chopping the curve up into many much smaller pieces. The mass of one of the bits is going to be the mass density evaluated somewhere within that bit times the length of that bit. I'm using lowercase script s for arc length, not to be confused with capital S, which is surface area. In all of our different ideas about integration, we take the region that we're interested in, divide it up into smaller regions. We have some measure of how big these regions are in one sense or the other, and we let the norm of the partition be the largest of those sizes. As usual, then, I'm going to let the norm of the partition be the biggest arc length amongst all the subdivisions. The total mass is going to approximately be the sum of our approximate masses. I need to sum up these quantities and take the limit as the norm of the partition tends to 0. This is the same game we've played quite a few times already. So it comes as no surprise that we're going to make up a name for this limit. We're going to call it an integral of some type. This time, though, I'm not integrating along the x-axis or with respect to area in the plane or anything. I'm integrating with respect to arc length along the curve. The symbol that we're going to use for this is integral sign, name of the curve, the function that we're integrating, d lowercase script s, integrated with respect to arc length. We pronounce this as the line integral of f of x and y along curve C. In the past, we have made similar definitions, and then the immediate question we have to answer is, how do we evaluate such things? If you remember from chapter 11, the magnitude of the derivative of the position is the rate of change of arc length with respect to time, meaning that the amount of arc length over the amount of time, this is an actual fraction now, is approximately the value of the derivative. So the change in arc length is approximately the magnitude of r prime at t times how much you change the t. If we have parametric equations in 2 dimensions, the velocity vector is just the derivative of the position vector. So using the dot notation this time around, take the derivative of x with respect to t, square it, take the derivative of y with respect to t, square that, add them together, take the square root, multiply by dt, that is ds. That's the differential of arc length, and we will be multiplying by mass density. The limits of integration on this integral are going to be the smallest and biggest t values that are relevant to us. If the curve is smooth, we can just do it this way. If it's piecewise smooth, we would have to chop it up into several smooth chunks. So, for example, I'm going to start at the origin. I'm going to travel in a straight line to the point x equal 1, y equal 1, and I'd like to find the line integral along curve C of x with respect to arc length. Now, notice I have particular formulas for the x and the y. That's necessary. If I just give you the picture, I haven't described the curve fully, but here, x will be t, y will be t will vary between 0 and 1. The derivative of x with respect to t is 1. The derivative of y with respect to t is 1. If you square those and add them up, you get square root of 2. So the ds is going to be square root of 2 dt. Then I have to put in the thing that I'm integrating. I'm integrating x, but x in terms of t is just t. So the integral that you have to do is the integral from 0 to 1, square root of 2 times t integrated with respect to t. That's straightforward to integrate. You get square root of 2 over 2 for an answer. Of course, starting at the origin and ending at x equal 1, y equal 1 can be achieved in ways other than the straight line path. For example, you might move along the parabola y equals x squared. The easiest way I can think of parametrically describing that is x equals t, y equals t squared. T will still vary between 0 and 1, but this time I'm not looking at the same xy points as I were on the first one. So it may very well be true, and will be true in this case, that the integral will work out to be something different from what we had in the first example. If you look at the derivative of x, it's 1 again. The derivative of y is 2t though. So x equal t is the quantity that I'm integrating. This is ds. I've written it in terms of an ordinary integral with respect to t, and t can be as small as 0 or as big as 1. You can actually do this integral in closed form solution by using a u substitution, where u is 1 plus 4t squared. After you do that, though, you'll get this for the antiderivative. One can insert t equals 0, t equal 1, and subtract. In this case, I expressed my answer in decimal at the end. It's about 0.84836. The answer we got along the straight line was radical 2 over 2, which you'll remember is about 0.707. So we got different answers because we're using different xy points. And not only that, the curve isn't even the same general kind of shape. So generally speaking, if you evaluate one of these line integrals, it depends on the details of what curve you're traveling along. A question that's going to be of interest to us is this: are there any situations where that's not true? Are there any situations in which this integral that you calculate doesn't depend on the shape of the path that you took? It turns out that the answer to that question is yes, there are, but we'll see that soon. First, though, we always start off with easy things. So we've talked about mass of a wire. We interpret the function that we're integrating along a curve as a mass density. That's not what we're really interested in, though. We want to talk about the line integral of a vector field. I want to imagine that I've got some force field for every xy in the plane, or every xyz in three-dimensional space. I've got a force field vector. Maybe it's gravitational or electrostatic or some such thing. I'm going to move an object along a curve, C, so I'll have the picture of the points and parametric equations describing the graph. I want to figure out how much work is done. So imagine I've got a curve like that. By now, it should be obvious what we're going to do. We're going to do the same thing we always do. We carve the picture up into a bunch of much smaller pictures so that I can pretend that the passage along the curve is a straight line. So we're going to magnify up chunk number I. The beginning point corresponds to t number I minus 1. The ending point corresponds to t equal ti. And I'm going to chop it up so small that this looks like a straight line to me. Also, I'll chop it up so small that the force doesn't have much of an opportunity to change on each small subinterval. Now, long ago, we studied work in the sense of displacing an object in a direction parallel to the force. Later, we figured out we don't have to restrict ourselves so much. The amount of work that goes with chunk number I is the vector dot product of the force on chunk number I with displacement, change in position, number I. Now, we're going to have some way of calculating things, so it's worth mentioning that I can write this down in at least three different ways. I can literally just leave it as force dot displacement, or I could write it as force dot rate of change of position with respect to arc length times difference in arc length, or I could write it as force dot product derivative of r with respect to t times delta t. If I write it in that first way, that's going to be the definition of our symbolism. We'll call it the line integral over curve C of force F. Because derivative of r with respect to s is the unit tangent vector, I could use this format and say derivative of r with respect to s is the unit tangent vector. So this would be an integral with respect to arc length along the curve of what I get when I dot product the force and the unit tangent vector. Or what's usually most convenient is I'll add up all the contributions of things like that and let all of the delta t's tend to zero. The t has a specific beginning and ending value if I know my curve. So I'll integrate from t equal a to t equal b with respect to t of the force vector dot product with the velocity vector. That last one is very convenient. So suppose an object is acted upon by a force field. At point xyz in three-dimensional space, the force vector from the force field is x squared y times I plus x minus y times z j plus z squared y times k. I'm going to move the object along a path where x is t, y is t squared, and z is also t squared. I'm going to do this starting at t equals 0 and ending at t equal 5. I want to figure out how much work is done. If I take my formulas for x, y, and z and convert them back into a vector valued function, x is t, y is t squared, z is t squared, then the derivative of that is 1 times r plus 2tj plus 2t times k. If I want to calculate the line integral, it'll be the integral from 0 to 1 of the force dot product with the velocity vector integrated with respect to time. The force is given by this vector valued function. The RDT is given by this vector valued function. If you do the dot product, you'll get x squared y times 1 plus x minus y times z times 2t plus z squared y times 2 times t. At that stage, it looks like we're mixing apples and oranges, but we're not interested in any old x, y, z. We only care about those points on our curve. So on the curve, x is t, y is t squared, z is t squared. If you put those values into this expression, you find out that force dot product with the velocity vector can be written just as this expression involving t. After putting that into my integral, I find out that I just have to integrate a polynomial function in terms of t. The antiderivative is easy enough to get. When t is 0, the entire antiderivative is 0. So when t equal 1, you get the only part that contributes. In decimal, in the end, it's about 0.086339. We have already seen that the exact shape that you travel along makes a difference in these line integrals. More interestingly, the orientation matters too. I'm going to start at t equals 0, end at t equal 1. My curve will be x equal t, y equal t for those t values. This gives me that same straight line segment that starts at the origin and travels out to the point 1, 1. If I use the setup that we have described, then the line integral is going to be the integral of the dot product of f dot dr, which is the integral of the dot product of the force vector with the velocity vector, derivative of t is 1, integrated with respect to t. I write this in terms of x and y, but I know what x and y are in terms of t. 3 times x times y is 3 times t, 3t squared. plus y squared. That would be plus t squared. So you're going to be integrating 4 times t squared. That integral is easy to do. It works out to be 4/3 units, units of energy or work. But now look at this curve. X is going to be 1 minus t, y is going to be 1 minus t. T is still going to vary between 0 and 1, but this time, when t is 0, x and y will both be 1, which means I'm starting here. And when t is 1, x and y will both be 0, so I end up there. I'm traveling along the same set of points as the other one, but I'm doing it in the opposite direction. The derivatives of x and y are easy to work out, as before. This time, though, when I simplify the integrand with respect to t, I get 4 multiplied by t squared minus 1. Carrying out the integral, it works out to be negative 8/3, which is different from what I got the other way. This is very strange. This says the amount of work that it takes to go from the origin to the point 1, 1 along a straight line, and the amount of energy it would take to go from 1, 1 to the origin along a straight line are different from each other. So this is going to have some consequences for us when we talk about conservation of energy. In our previous work in calculus, we've had certain standard things that we would do that were just for convenience. We know perfectly well that derivatives are not fractions. So when I say dy dx is 3x plus 1, for instance, I don't mean that some number dy divided by dx is this. However, it's sometimes useful to pretend like it is. We do things like this when we do integration by substitution, integration by parts, also certain applications of the chain rule. So I'm going to refer to this as the standard abuse of notation. Likewise, if I have x and y as functions f of t and g of t, the derivative of x is f prime, the derivative of y is g prime. We will have the standard abuse of notation. When I write the symbol dx, I mean the derivative of x multiplied by dt, and likewise for dy. Sometimes, especially in physics, people will write line integrals in a different form than we've written them. So I want to at least mention that and use this opportunity to abuse the notation in the usual way. A line integral along a curve, if I knew the explicit beginning and ending t values, I would just say the integral from a to b of the dot product of the force with the velocity vector, and I would do the integral and get my answer. I'm thinking in 2 dimensions now, just for convenience. The force is going to be some function of x and y times I, plus some other function of x and y times j. The components of the velocity vector are dx dt and dy dt. If I do the dot product of the force with the velocity vector, I could write that as m times dx dt plus n times dy dt, and then I would have to integrate that with respect to t. If you want to think of it this way, you could think of having 2 integrals, because the integral of a sum is the sum of the integral, and then we're going to use horrible notation. Dx dt times dt, we'll just write that as dx, and dy dt times dt will be written as dy. So I could write my integral as the integral over curve C of m dx plus the integral over curve C of n dy. We've pretended that the differentials are multipliers in the past. So now we'll pretend that the integral sign is that as well, and write this as the integral over curve C of the quantity m dx plus n dy. Really, even if you're willing to accept the abuse of notation, this should have parentheses around it. Many times in textbooks, though, they will omit the parentheses, making this much more mysterious looking than it actually is. And of course, in 3 dimensions, you can write something similar, except you'll have to have the z component part of the force. So I'd like to find the line integral over curve C of 3xy dx plus 2 times the quantity x plus y dy, where C is this curve. X is going to be t squared, y is going to be t cubed. The t will vary between 0 and 2. The derivative of x is 2x, so dx is 2t, pardon me, the derivative of x with respect to t is 2t. dx then will be 2t dt. Derivative of y with respect to t is 3t squared, so dy will be 3t squared dt. I need to figure out what 3xy and 2 multiplied by the quantity x plus y are. 3xy is 3 times t squared times t cubed. That would be 3 times t to the 5th power. 2 multiplied by x plus y is 2 times t squared plus 2 times t cubed. So this is m, this is dx, this is n, and this is dy. So abusing the language in the standard way, factor the dt out to the right, and you're left with an ordinary polynomial integration problem to do. If I've done my antiderivatives correctly, this is 321.82857. My point in talking about that last bit is you'll see line integrals written this way. It makes it look mysterious, but there's less there than meets the eye. I hope everyone's having a good day. I'll talk to you again real soon.